Every bridge begins with a single, unyielding problem, a gap. The earth drops away, and we need to cross. But gravity is relentless, and it demands a toll. The most instinctive solution is a beam bridge, a single straight line drawn between 2 points. It looks perfectly stable, but as a massive load rests on its center, a hidden physical battle begins. Weight doesn't just push down, it dramatically distorts the material. The top edge of the beam is violently squished together, an inward force called compression. Simultaneously, the bottom edge is forcibly stretched apart. That's tension. When these invisible forces overwhelm the material, the battle is lost. The top crushes, the bottom tears, and the beam snaps. To survive this crossing, we must outsmart the forces with geometry. To survive those invisible forces, engineers change the geometry. A simple square frame simply folds under pressure. But the triangle is inherently rigid. Press down on the peak, and the two angled sides compress, pulling the base tight in tension. The shape holds. If a single flat beam sags over a gap, we reinforce it with a continuous web of these balanced triangles. This creates a truss. The simple beam is instantly transformed into a rigid, load-bearing structure. The magic of the truss is distribution. When weight hits the deck, the interlocking triangles share the burden. The force is channeled outwardly through the geometry. The top beams compress, the bottom deck pulls in tension, perfectly splitting the load out to the rock walls. But there is a strict limit. If we try to cross a much wider gap by simply stretching a truss across it, the sheer amount of heavy steel becomes a trap. Eventually, the bridge becomes so massive that it buckles under its own dead weight. We need an entirely different geometry to beat the distance. To cross these massive gaps, we have to stop fighting gravity and start using it. The arch abandons the flat beam entirely. It's a brilliant geometric trick. When weight presses down on the peak, the curve prevents it from bending. Instead, that downward energy is squeezed sideways, flowing all the way down into the earth. Because of this redirection, every single piece of the arch is being pushed together. This is pure compression. With almost zero tension to tear it apart, heavy, brittle materials like stone or concrete become practically indestructible. But there's a catch. An arch relies on massive rock abutments to catch all that outward force. And when the gap you need to cross isn't a river, but a sprawling ocean channel, there's nowhere to anchor the curve. To cross open oceans, the rules of geometry change. An arch or truss cannot reach that far. The structure would bend and shatter under its own crushing weight long before reaching the other side. To conquer these monumental spans, engineers build up. Colossal vertical towers are planted deep into the bedrock below. These massive columns handle pure compression, channeling the immense weight directly downward into the unyielding earth. Then comes the brilliant stroke, a sweeping main cable draped over the high peaks, pinned to massive anchorages on either shore. This cable is under extreme tension, a colossal tug-of-war balanced in mid-air, transferring the massive pull back to solid land. From that main arc, thin vertical cables rapidly stitch downward, catching the heavy road deck. The structure becomes an intricate web. Traffic pulls down, but the heroic tension of the vertical cables pulls right back up. It is an absolute triumph over immense distances, a perfect geometrical battle against gravity. But out over the open water, gravity isn't the only invisible force trying to tear a bridge apart. Out in the open, the most destructive threat is entirely horizontal. When lateral winds strike, a rigid bridge becomes a massive sail. The wind doesn't push down, it pushes sideways. If a bridge acts like a solid wall, those winds create deadly resonance, twisting the steel until it literally tears apart. The solution isn't more mass. It's shaping the deck so the wind slices cleanly around it, neutralizing the force before it catches hold. A bridge is never truly static. It's a breathing machine, locked in an endless battle to master the forces of nature. So next time you cross one, remember, you aren't just driving over dead steel. You are riding inside a masterpiece of perfectly balanced tension and compression.